Or in other words, given epsilon, you choose epsilon prime such that epsilon prime is equal to epsilon divided by 2m plus b minus m. That's how you do it. And then work it, estimate for this or that epsilon, and then eventually you will get epsilon prime will be replaced by epsilon divided by this. Therefore, we get now therefore f is Riemann integral. Now just review the whole proof and see where exactly we have used the fact that D is a null set. Okay? So that's how you critically look at this problem. Okay. Now I suggest a few results which you can attempt to prove and be a good exercise to do. Now, so we give some exercises. You have to put your hand on that. These are exercises proposed in Riemann. Let D containing AB be an null set. Then AB slash D is the suggestion is that you assume this is not dense. In that case, you arrive at some combination. Second, let f is a Riemann integral function of D. Such that the set one set, then show that same sort of technique that you can use to prove this. Okay. The third observation is, we have already proved this earlier, that look at the function which is a Riemann integral. Look at the class of functions which are Riemann integrals. So Riemann integral on possessive locus. And right here is where the next problem that you want to show is that Now, what you want, what you want, what you want, what I want to say. A real linear space means a linear space over the field of reals. That's a mean. Okay. Then also look at this map. And call it, it's called there are two things to do. I think we have proved it already. Sum of Riemann integrable functions is Riemann integrable. Scalar multiple of Riemann integrable function is again Riemann integrable. And then of course all the properties of the linear space are satisfied there. That is existence of some is of course associative, commutative, and then you have got all the requirements of a linear space are satisfied by RAD. That's what you have to prove. And then you look at this map. Now this map can be looked upon as a map TF from RAD to R. It's a scalar valued function. Then you prove that TF is linear. So TF of alpha F plus beta G equal to TF alpha TF T. Okay. Alpha T of F plus beta T of. This is what you have to do. That's quite easy. So it's a linear space and this is a linear function. It's an important function. Okay, the next property is that all non-negative functions. Then what you have is that then integral a to b that is one simple to prove. Secondly, if the set for which the effects is strictly positive, that's also difficult. So there are two parts for this, one second part. Now, a immediate consequence of this is that let the bounded functions on AB such that F belonging to is Riemann integrable on AB. F comma G belong to R. Let the set of all X for which Fx not equal to Gx is an RC. Then now you can also ask the following question. Suppose F is Riemann integrable and nothing is said about G except that they are bounded functions on it. And let this set be a null set. Can you say that G is Riemann integrable and this property is satisfied? So that's another question that you must. Okay. You can explore with some examples. Let me write that part. What's the next question? Both F and G are Riemann integrable, then this is true. Otherwise, you can ask this question. Of course, it's quite simple to get. Because if F and G are Riemann integrable, then F minus G is Riemann integrable. And write H equal to F minus G. And then apply the previous result. You will get that. Okay. Now this you explore. Exactly. So that's something to be. So there we are assuming F is Riemann integrable, but G is, we don't know, it's just a bounded function. And then see what happens. Okay. But I will, I give enough examples to explore that. There are functions like the Dirichlet function, which is not Riemann integrable. You have the popcorn function, which is Riemann integrable. And this kind of functions are there in your hand, so you can use some of them and or a combination of them and then try to get the information. Okay. So this is something which we have mentioned earlier. G is a Riemann integrable function, and F from n to capital N is continuous, then H defined by F composition G Riemann integration. Now the question is, having proved this, you ask the question, suppose you relax this to F is also Riemann integrable. Is G F composition G Riemann integrable in that case? So that's the next question. And there in that context, possibly the popcorn function is useful. Okay. So let us take let and gx equal to 1 if 0 less than x less than or equal to 1 and g0 equal to so that's a fairly straightforward function, which is 1 everywhere except at 0. So just only one discontinuity, and therefore G is a Riemann integrable function. F is also a Riemann integrable function because it is given to be the popcorn function. Now consider find out what this function is. Okay. So the question is so if this is not, that you can see by actually computing h. So compute h and see whether what function it is, and you can immediately probably infer that this is not Riemann integrable. Also, what does it say? It says that if both f and g are Riemann integrable functions, then and g composition f is well defined, then still you cannot say that g composition f is Riemann integrable. That is not true. So you can't relax this any further. So G is here, we have assumed G is to be continuous, and that is required to support that result. So two Riemann integrable functions well defined, and G composition f, if you take, well defined in the sense that G composition f makes sense, then G composition f need not be Riemann integrable. That is the conclusion from that. Okay. Now there is another result that we have already proved. All monotone functions, let on AB. Then now one of the results that leads to this is that you see the set of all what did I wanted to say something. So this can have at most countable discontinuities. That's something that comes like this because you are assumed without loss of generality is a monotonically increasing function. And at each discontinuity, you can actually show that this is a simple discontinuity. Then, given two numbers of the limits, you take the point xi. So xi minus the limit as xi tends to 0 from the right and from the left of the function are different. Then you see that between them you can choose a rational number. So this you can do at every discontinuity. It's a monotone function which you use that. So all these rational numbers that you choose can be chosen differently. Okay? Therefore, what do you get? Get that? Just at most countable number of discontinuities. That's very simple. Okay. Now I think I'll stop here today, and then what we explore next is in fact we have completed now one of the second question that we have explored. So what were the questions that we explored earlier? First explore the connection between the area function and the what you call the antiderivative of the function. So that is the fundamental theorem of calculus. Now the second problem was, of course, which functions are Riemann integral, and that also we have resolved. So two major questions we have already tried to explore. Okay. Now we embark on a very fascinating set which gives you a wealth of examples for all pathological cases. And this is the well-known Cantor set. Just some amazingly beautiful properties. And that, of course, these properties are offshoot of the mysteries that lie on the structure of the real life. Okay? So we'll do that next time. So we start with the Cantor set next time. Okay? And after completing that, our strategy or our next goal is to make some observations on what are the inadequacies of the Riemann integral. That would justify our next step, namely going to go for a more general definition of integral, so that more functions can be brought into a class than what the Riemann integral accommodates. Okay, which leads to the startling discovery of the last century, namely better integration theory, and now its various generalizations. So thank you very much.